the weak star, topology on N star. The weak topology on N, strong topology on N. Strong topology on N star. The metric topology arising from the norm on N is called as strong topology on N. The basis for this topology is script B, and script B is nothing but consisting of B, D, X, comma, epsilon, such that X belongs to N, epsilon greater than 0. If T belongs to N star, which is BNF, the field where F is R or C and T is a bounded linear map, that is, T is a map from N to F. T is linear. T is the four equivalent condition: continuity at a point, continuous everywhere, norm of Tx is less than equal to k times norm of x, there exists such a k real number, and the unit sphere, closed unit sphere, is bounded, continuous. There is an alternative formulation for the continuity. The topological, as we have seen in earlier lecture, topological definition of continuity is defined using open sets of codomain. Inverse image of open sets is open under the map between two topological spaces. Then such a map is said to be continuous. Note that the epsilon delta definition in metric space and sequential definition are equivalent to topological definition. Since T is a map from N to F, F is R or C, the topologies on R or C is the usual topology. So if this is a straight line R, then if 2 points are there, X and Y, the distance between X comma Y is defined to be mod of X minus Y. In fact, so this is a metric on R, and the basis for usual topology is of the form x minus epsilon to x plus epsilon. This set x belonging to R and epsilon strictly greater than 0. So any open set in R is a arbitrary union of these kind of intervals. That is the definition of an open set in R. Similarly, an open set in F is as follows. So let's draw the complex plane. This is I minus I is on this side, 1 minus 1. So this is real and this is imaginary axis. So if you take any point over here, maybe say Z, so if you drop a perpendicular over here, if this is alpha and if this is beta, and this point Z is alpha plus I beta. And if we are looking for at this point, you have a radius greater than 0. Look at the ball centered at this thing with the usual distance. So the distance between, maybe say Z is here, there is some another point, maybe say Z dash, that is C plus I D. Then the distance between Z and Z dash is given to be square root of alpha minus C whole square plus beta minus D whole square. This is the distance, this any 2 points. So the basis for this metric topology on C is given by the ball centered at any other point with radius. So it would be what? It would be nothing but collection of all those complex numbers u, such that the distance between Z minus u is strictly less than epsilon. If you are looking for this thing, this radius is epsilon is strictly greater than 0, and Z is any complex number. So you are looking for all such u with our complex number. And again, any open set here is union of these kind of basis elements. So once we have the idea of what are open sets on the field, which is either R or C, what does the T does? The T takes an open set. So whatever the given F is there, R or C, it depends whether the N is a real vector space or complex vector space, whatever, this is the thing. And so T is a map N to F which is linear and continuous. Then we are looking at open set. So U is any open set in F, then T inverse U is open. Why this is so? Because the topological definition of continuity. Since any open set, F is a metric topology, that is defined. So the basis for this thing is open balls. In this case, it is open intervals. In this case, it is a open disk centered at point with positive radius. So what we can specify is that T inverse of a typical basis element BD, maybe say alpha comma epsilon, that must be open. That is a required condition, and that is satisfied if T is continuous, where alpha is a scalar and epsilon is strictly greater than 0. It's a real number. T is continuous with respect to the norm topology on N. However, there may exist a coarser topology than the metric topology under which the function t is continuous. Even more, as a set n star, which is b n comma f, we look all functions over here in n star. N star, once defined, is a set. And next, considering its elements as merely linear functions and looking for coarsest topology on N to make all of these functions continuous. Subbasis is an simplest way to define a topology on a set with required properties. In particular, we consider the following set. Set T inverse of BD x comma rather alpha comma epsilon, where alpha belongs to the field F, epsilon is strictly greater than F, and T is varying in n star. To collect this set, this set is a subset of N. Note that this is in fact a set theoretic inverse. As T is not given to be 1 1 and onto, but by definition of function each point has an image on right hand side. So the set forms an cover partition of N and hence qualifies to be a basis, rather sub-basis, and all of the functions T would become continuous since we have taken inverse images of basis element. So this makes all functions in N star continuous and N gets a topology that is coarsest, thereby it is weaker than the norm topology, and this topology, coarser one, is called by the name the weak topology on N, and the norm topology is called as strong topology. As the case is, we can look at the space n star star, which is B of n star comma f. So we have similarly the weak topology and strong topology on n star. So if you take capital F belonging to n star star, so capital F is a map from n star to F, the field, which is linear map and continuous with respect to the metric topology on n star, that is the supremum norm on n star. So if you take any f belonging to n star, the norm of f is nothing but we have seen the supremum of mod of f of x such that norm of x is less than equal to 1, x belonging to n. Similarly, the weak topology is on n stars is the coarsest topology that makes the functions of n star star continuous. So the coarsest topology on n star that makes functions in n star star. So here these are elements of n star star. Each of this element is a function from n star to f. Makes continuous is called as the weak topology on n star. We have seen a correspondence that n is sitting as a copy in n star star if n is not equal to n star star by the map sending x to f subscript x, where f of x is a map from n star to the field f. Fx of f is equal to f of x. This is the definition where f itself is a map from n to f. So the point is acting. So the function on a point can be thought as that a point is acting on all functions. One function acts on all points. So if you fix a point and vary the function, then you get a corresponding fx. And we have seen that this is isometric isomorphism. So the map over here is 1, 1. And it's a linear and it's continuous mapping sending x to fx. However, if n is not equal to n star star, means if there exists g belonging to n star star such that no element of n produces g, then n is not a reflexive space. So if a space is reflexive, that means that n as this kind of identification is equal to n star star. So there are criterion regarding reflexivity. So we will consider non-linear space and we will consider the closed unit sphere in n star. look at a simpler criterion for that. We also, as a tutorial, would work out on the fact that is the compactness of the unit ball in n star, and that is in the case where n is finite dimensional. And the reflexivity also shall be dealt, that the space is reflexive if the closed unit ball is compact in the weak topology. So let's, rather n star star, we will focus on the functions arising. So we have two topologies, weak topology, strong topology. So there is another topology which is to a subclass of functions which are arising from n. If n is equal to n star star, then the things are okay. Then the weak topology is in fact not only it is the weak topology of n star star, but also of n as a copy in n star star. If there are functions which are extras, in other words, they are not generated through the points in n, then what do we have? We can do the following thing, is that we can consider this subclass of functions and we try to look at the coarsest topology on n which make these functions continuous, and such a topology on n star is called as the weak star. So let's write the word first, what we are dealing with. The weak star topology on n star. So the coarsest topology on n star that makes the function fx as a sub this set h continuous. Such a topology, it can be defined with respect to what, taking basis set in the field, taking inverse images under these restricted functions, which are what, subclass of functions from n star star. And if you take this thing, then take the inverse images, and what do we get is the coarsest topology, which makes this subclass of functions to be what, continuous. These functions are also continuous in the weak topology. The weak topology considers even some more functions. So here we are having, if it is not a reflexive space, lesser number of functions, and we are looking at its inverse images of this basis element, and we are making then a sub-basis out of it of n star. This sub-basis, what it generates the topology, is called as the weak star topology. So what do we have is that every weak open set would be what? It's open. It is in fact a union of elements of some more functions. So some more functions are there, and here these in the weak star topology, it's the inverse image of these functions fx. So the strong topology is there. These are already continuous, and so on. So the strong topology is stronger than the weak topology as well as the weak star topology. The basis element of the weak star topology are in fact the sub-basis element of the weak star topology. They are also contained in the weak topology. So the weak topology contains more open sets. So the weak star topology is in fact coarser than the weak topology on n star, and the strong topology is the strongest topology in the sense that all of these functions are already continuous, inverse image, so it has some more open sets, the possibilities. So weak star topology is contained in weak topology is contained in strong topology on n star. So these three topologies exist on n star. On n there exist only two topologies, weak and the strong topology. The weak star arises on n star, and it is arising out of the fact that looking at the point and a function on which are from n star star arising from n. The sub basis over here can be written. So what would be the sub basis for the weak star topology? On n star. So let's consider a symbol S capital Fx F naught epsilon, where Fx belongs to n star star and x is in n. So this Fx arises from this x in n, and F naught is a map in n star which is BNF. So this in fact can be rewritten as just a symbol. So we'll see what is this thing. So S, because Fx is identified with x and norm of x is the same thing as norm of F subscript x. So we have S, X, F naught and epsilon. So we have to look at inverse image of a basis element of the field. So because, so just rub the top part. So let's consider the following. If I have any F belonging to n star, consider Fx of F minus Fx of F naught. So Fx rather here F naught and Fx of small f. Small f modulus of this thing if this is strictly less than epsilon. So if you consider Fx of F naught minus Fx of F, so this is nothing but, so F naught is a fixed object, Fx is there, epsilon is there, these are all fixed objects, this is just a real number, epsilon is strictly greater than 0. The point is that if your field capital F is real, then this just becomes what? This just becomes your, so the Fx of F belongs to what? It belongs to an interval. So by definition, so Fx is just the absolute value belongs to Fx of F naught minus epsilon to Fx of F naught plus epsilon, open interval. Okay, so it is just Fx of F belonging to Fx of F naught minus epsilon to Fx of F naught plus epsilon. Okay, so this is the case. Then by definition this is nothing but F naught of x minus epsilon to F naught of x plus epsilon, and this is what this is Fx belonging to, in case our field is real. If it is a complex field, Then this a typical basis element. So this is an interval centered at what? At f naught, fx of so at f naught, and with radius what? Epsilon, f naught of x, centered at rather f naught of x. In that case, it would be, in the case of the complex, it would be just like the disk on the complex plane, and here would be your point f naught of x, and f of x would be somewhere here. F of x is an interior point, except the boundary, all the interior point. So this would be the basis. So what is the symbol then? S. So the symbol S stands for S x f naught is nothing but the collection of all these f belonging to n star such that mod of, this is absolute value or modulus depending upon the real or the complex case, fx of f minus fx of f naught strictly less than epsilon. Rather, let's just write here, so as a space, so it would be equal to collection of all those f belonging to n star such that mod of fx of f minus fx of f naught. So you take this thing, so these kind of s, x, f naught and epsilon, you can clearly see that this x is belonging to n. So this fx is belonging to n star star. So for all points these are defined, fx belonging to n, you have taken an f naught which was a typical element in what? In n star, and epsilon was any greater than this thing. So this forms a sub basis for every point in n star. So in n star we have f naught, so you can clearly see that fx of, if I write f naught here, f naught minus fx of f naught, that is 0. So that is also, so for, because it is a ball centered at f naught by fx. So what do we get is that for every point I have this thing which is covering. So if you collect all of these covers, then what do we get is that for one particular fx, if you fix your x and epsilon and just move your f naught, this is in fact a covering for all n star. Now what do we do is that we take f, capital F subscript y also, collect all of these functions which are arising from this thing. So this kind of things, sets, they will be making what? F continuous. So inverse image, so property of subbasis is what? Every element of the subbasis is open in topology generated by subbasis. Similarly, every element, every set which is generated by by a basis for a topology is open in topology generated by the basis. So what do we have is that this is in fact S, x, f naught and epsilon is a partition for n star and forms a subbasis. Not only subbasis, but this subbasis is a special, it is the coarsest topology that makes objects of n star star arising from n continuous. So we have got the three topologies on n star star, the weak star, the strong topology. In fact, let's look at the structure of this weak star topology. So what is the structure of the weak star topology? So the weak star topology on n star, this is our claim or remark that n star is not only Hausdorff in the strong topology, because every metric topology is a Hausdorff topology, is a Hausdorff topology, is the Hausdorff space, in weak star topology. So this is the coarsest topology on n star. In other words, all the elements of the weak star topology are, all open sets are open in the weak topology also and in the strong topology also. So this is a Hausdorff space. So there is a separation here. So if you look at any two subbasis element, then what we can do is that we can find a separation for this thing, so for distinct points. So suppose f and g are two functions belonging to n star such that f is not equal to g. So these are linear functions. They are maps from n to the field. That's the definition of n star. So what do is that we take, since f is not equal to g, this is given. Since f not equal to g, there exists a x belonging to n because they are defined on n such that fx is not equal to g of x. At least one such thing is there. So the moment fx is not equal to gx, what can be done is that this distance is a positive distance, which is fx minus gx. If you consider this, it's a scalar, so you consider this mod of this thing, this would be strictly greater than 0. So call this distance as epsilon. This distance is epsilon. So you have, if the moment you have this thing, take epsilon by 3 of what? If you look at s x comma f comma epsilon by 3 and s x comma g comma epsilon by 3, these are the two neighborhoods. This basis set what was defined, it was the collection of all those functions in n star such that fx minus hx is less than what? Epsilon by 3. And if suppose u is the function in this s x comma g comma epsilon by 3, all those functions whose gx minus that hx may be here also rx is this also, gx minus rx, that is less than epsilon by 3. So the distance between fx and gx is what? It's an epsilon. So what do we get is that epsilon by 3 is that. So its intersection is a non-empty. It's easy to see, but rather we can write also. So what would be the proof? So suppose there is a common element and we'll come to a contradiction. Let s x comma f comma epsilon by 3 intersect with s x comma g comma epsilon by 3. Okay, non-empty. So suppose h is there. So h belongs to s x comma f comma epsilon by 3. H also belongs to x comma s of x comma g comma epsilon by 3. So the distance, so by definition what would happen is that fx minus hx, mod of fx minus hx, this is less than epsilon by 3. Mod of g of x minus hx, this is less than epsilon by 3. And if you look at mod of f of x minus g of x, so we can do add and subtract h of x, fx minus hx plus hx minus g of x, and then apply the triangle inequality. So mod of f of x minus h of x plus mod of h of x minus g of x, this is what? Less than epsilon by 3 plus epsilon by 3, that is 2 epsilon by 3. So what we are getting is that this distance is less than 2 epsilon by 3. But what was in fact this epsilon? The definition, by definition, this distance was epsilon. Epsilon can never be, epsilon is strictly greater than 0. So what we are getting is that 3 epsilon is strictly smaller than 2 epsilon from here, or epsilon is strictly smaller than 0. That is a contradiction. So from here and here, what we get is that 3 epsilon is strictly smaller than 2 epsilon, or rather epsilon is strictly smaller than, there is a contradiction. And this is arising because we are assuming that these two intersection is non-empty. In other words, these two sets, which are objects or sets of subbases, they are open in weak star topology, and these two things do not intersect. So if two functions are distinct, then we can find two distinct neighborhoods in the weak star topology which separate these 2 points. So in other words, the weak star topology is the Hausdorff topology. And since weak star topology is a Hausdorff topology, every open set in weak star topology is contained in the weak topology, because the n star star contains some more, may contain some more elements if it is not reflexive. So all the functions which are arising from n, they are capital Fx, they are also in n star star, but it may have some more. So what we have is that the weak star topology is the coarser than the weak topology, and the weak topology is coarser than the strong topology. But if we can find a separation in the coarsest topology of two functions, so what we have is that this also shows that the weak topology is also the Hausdorff space. The proven fact is that every metric space is a Hausdorff space. So what do we have is that the condition for Hausdorffness. So the weak star topology is a Hausdorff space. We can consider later convergence, as we have seen in the norm-linear spaces of the sequence xn converging to x, the convergence in the norm. We can also talk of the convergence in the weak topology. We can also talk of the convergence in weak star topology. All of these things can be discussed. So S, the unit ball, closed unit ball S, we have seen in N, which is the collection of all those x with that norm of x is less than equal to 1. S star would be denoted the collection of all those functionals in N star whose norm is less than equal to 1 in the supreme of norm. So we'll consider the unit ball and the criterion with respect to strong topology, with respect to weak topology, and the reflexivity also. And we can also come to the fact of considering that if a given non-linear space and the closed unit sphere is there in N star, so the criterion that what happens if you have the weak star topology, it's a compact Hausdorff space. In real analysis, you have seen that every compact set is a closed and bounded. But here, as we have seen in a Hausdorff spaces, closed subspace of compact spaces are compact. Compact subspace of Hausdorff spaces are closed. So it need not be the case that compactness always implies that closed as well as bounded, as the word is there. So in the compact Hausdorff spaces, if you look at closed subspace of compact spaces, so two words are there, compact and Hausdorff. In Hausdorff spaces, if you use compact subspaces of Hausdorff spaces become closed, and because the space is also closed, is a compact subspace, then what happens is that closed subspaces of compact spaces are compact and compact subspaces of Hausdorff are closed. So the closeness and compactness can be interchanged with respect to what compact Hausdorff spaces, as was seen earlier. So we'll come to a proposition later that looks at the structure of the unit ball in the weak star topology. So let's stop here. That's almost an hour. We can continue tomorrow. Thank you.